Hello everybody and welcome to video 1 of the capacitors topic. Now in this introductory video to the topic we're going to have a look at what capacitors are, what their function is within a circuit, and then we'll go on to have a look at how they're made. Now on the screen you can see there's a picture, and on that picture everything there that you can see is a capacitor. So you can see that they come in all kinds of different shapes and sizes, but regardless of that, their function is always the same. The idea of a capacitor within a circuit is that it stores charge. Now that charge can then be released at a later time, but the whole idea of the capacitor, as I said, is to store electrical charge. Now, where you'll find the most capacitors is on some kind of circuit board, and you can see just on the right hand side there is just a picture of a generic circuit board. You can see that we've got quite a few capacitors present on here. You can see that we've got some big capacitors here and here, some slightly smaller ones, but then you can see we've got here some even smaller capacitors. So just on that circuit board, I think a moment ago I counted that there were 15 capacitors just on that one particular circuit board. So depending on what kind of device exactly you're watching this video, whether it be on your phone, on your computer, laptop, tablet, whatever that's going to be, inside that device on the different circuit boards you'll find that you have quite a few capacitors inside, and helping you to watch this video right now. If we have a look inside a capacitor, then you can see that there are two main components that we need for a capacitor. Firstly, we need a pair of conductors, and on that diagram that's signified by plate A and plate B, both of which will be made of a conductor, probably by some form of metal. In between the two plates then we have what's known as a dielectric. Now the dielectric is an insulator, and you can see that it is between the two plates, and therefore the dielectric acts to insulate the two plates from each other. Now in commercial capacitors, the dielectric is probably made of some form of paper with a wax coating, or something along those lines, but you can even go as simple, if you know, to make a homemade capacitor or something like that, you can go as simple as using a plastic carrier bag or a bin bag or something like that, just any kind of substance that can insulate. Now the way that most again commercial capacitors are constructed is that those components, the two plates and the dielectric, tend to be very long and very thin, but hopefully you can see from the diagram that you take these very long, very thin conductors and insulators, and you then just roll them up inside each other. The two black bits here, so you've got number 1 there and number 2 there, those are the connectors to then make the capacitor part of the circuit. So let's now have a look at how a capacitor works within a circuit. So if we have the two conducting plates, so there is one of our conductors and there is the other conductor, and then in the middle we have the dielectric. Okay, and our two conductors. Now what we're going to do is we're going to take those two conductors and we're going to connect them to some kind of power supply. Okay, so we'll just say for now that that is just a simple battery or something like that. Now remember, when we have a battery, we know that the long end signifies positive and the shorter end signifies negative. And when it comes to current, we know that current, or conventional current, flows from positive to negative. But of course that's current. What we're more interested in is the flow of electrons, and electrons themselves, again being negative, will flow away from the negative end of the battery. They'll be repelled by the negative end of the battery, and they'll flow towards the positive end of the battery. So the flow of electrons is in that direction. Now, when we connect a capacitor to a battery, we're going to get that flow of electrons. What we'll end up with then on the right hand plate, as we've drawn it, is we will end up with a build-up of electrons. We'll end up with an excess of electrons on that plate there. On the left hand plate, because electrons have flown away from it, you'll end up with a deficit of electrons, and therefore you'll end up with a net positive charge. The function of the dielectric inside the capacitor then is to stop the electrons from moving from the negatively charged plate onto the positively charged plate. Obviously, if you have two different charges, there will be a potential difference in between those two plates, and a potential difference will, if it's high enough, cause electrons to move between those two plates, and therefore cause the current to continue to flow. And that's why we need an insulator in between. Otherwise, we've just got two plates, and with a big enough potential difference in between those two plates, the electrons can move across the gap. If it's filled with air or a vacuum or something like that, they can just very simply move across the gap and continue that current flowing. And obviously, when it comes to a capacitor, that's not the point. We want to store the charge on the capacitor rather than just have that charge flowing round and around and around. Now, as a very basic way of seeing how dielectrics work, obviously, as with any substance, the dielectric will have molecules in them. And molecules, we know, are or have the ability to be polarised. In other words, if you have just a general molecule, it will have a positive end, and it will have a negative end. Now, in most substances, the direction of the positive end and the negative end, in most cases, will be completely random. I'll just draw a couple of molecules in there. Okay, like I said, this is an extremely simplistic way of looking at it, but hopefully we'll get the idea. Okay, so those molecules will just be pointing, at least the positive and negative end of those molecules will be pointing in random directions. Now, with a dielectric, when we place the dielectric inside an electric field, those molecules, at least the poles of those molecules, all end up pointing in the same direction. So positive, 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 and negative, negative, negative. So we can see that when we get them all to do that, when we get all the positive ends of the molecules to line up and all the negative ends of the molecules to line up, that is known as polarised. Up the top then we have non-polarised. When the dielectric becomes polarised then, we end up with, on this side of the dielectric, therefore, a net positive charge. And on this side of the dielectric, we end up with a net negative charge. Now, if you think about what that then happens, what that causes in the circuit, the positive side of the dielectric will attract more electrons onto the negative plate, and the negative side of the dielectric will repel electrons from the positive plate. And so what we end up with is even more charge being able to be stored on these two parallel conductors. The better the dielectric is at insulating the two plates from each other, the more charge we can then store on the capacitor in total. Now, as I said, that is a very, very basic way of looking at how a dielectric works. In reality, it's a lot more complicated than that, but that's just to give you an idea of exactly what the function of the dielectric in a capacitor is. We can now start to define some terms. So the first thing we're going to do is we're going to have a look at capacitance. And the symbol that we use for capacitance is a capital C. Now, again, the idea of a capacitor is to store charge, and capacitance, at least in a basic idea at the moment, before we start to move on in future videos into more complicated terms of capacitance, the idea of capacitance is that it's a measure of how much charge can be stored. Like I said, we will define that slightly better in future videos, but for now we'll just take this idea that capacitance measures in a way how much charge we are able to store in our capacitor. Let's have a think about what different factors can affect capacitance then. Well, firstly, we need to have a look at the dimensions of the two conductors, the dimensions of the two plates. Now, hopefully, we can see, going back to the previous diagram, we can see and we can imagine that the larger that those two conductors are, the more charge we're going to be able to store on them. Now, the best way to measure that is to consider the surface area of the plates. Okay, so A is the area of the conductors, and in fact, if we're going to get even more technical, it's the areas of the two conductors that overlap with each other. And as we increase that area, we should therefore increase the capacitance as well. Next then, we need to have a look at how far the two conductors are apart from each other. So we're going to call that D, where D is the separation of those two conductors. Now, in order to maximise the amount of charge that we're storing on the capacitors, we also need to maximise the electric field in between the two plates, and therefore the electric field in the dielectric. Well, from the electric fields topic, we know that electric field E is V over D when we're talking about parallel plate conductors. And therefore, if we want to maximise the electric field and therefore maximise the capacitance, we need to make sure that D, the separation of the conductors, is as small as possible. So as D increases, the capacitance will therefore decrease. Now, when we combine those two ideas into an equation, at least into the start of an equation, the capacitance of the capacitor will be proportional to A over D. So we can see, obviously, from the first bit, we can see that C and A are proportional to each other, and from the second bit, we can see that C and D are inversely proportional to each other. So there's the start of an equation. C is proportional to A over D. Now that we've determined that relationship between capacitance and the dimensions of the capacitor, we now need to get rid of that proportional sign, turn it into an equation by putting in an equal sign and some kind of constant of proportionality. So let's do that straight away. So let's say that C is equal to some constant multiplied by A over D. Now that constant comes from the permittivity of the dielectric. Now that phrase permittivity we've heard before. Again, going back to the electric fields topic, we had epsilon naught as 8.85 times 10 to the minus 12, and then this unit Fm to the minus 1 farads per metre. And that epsilon naught was known as the permittivity of free space. Now, permittivity, we didn't really go into much detail when we did the electric fields topic, but permittivity of a material is a measure of the ability of that material to be polarised. So the higher the permittivity, the more able that material is to be polarised, and therefore the better it acts as a dielectric. Now, the better it acts as a dielectric, the more charge we are able to store on the capacitor, and therefore the higher the capacitance will become. So as this idea of permittivity increases, it becomes better as an insulator, so therefore the charge that we can store increases, and therefore the capacitance also increases as well. We now have the constant of proportionality. The constant of proportionality comes from the dielectric and is just the permittivity of the dielectric. We can insert that into the equation, and we end up with the equation C is equal to epsilon A over D, where epsilon is the permittivity of the dielectric. Now, when we look at the equation C is equal to epsilon A over D, epsilon here, which we said was the permittivity of the dielectric, most of the time you will see that referred to as absolute permittivity. Now, we already know one permittivity for a medium, which is epsilon naught, and is the permittivity of free space. In other words, that is the permittivity of a vacuum. As a number, we know that that is 8.85 times 10 to the minus 12 farads per metre, and is obviously a constant. Now, what that does though is it gives us an idea of the kind of values and the kind of orders of magnitude that we expect absolute permittivity to be. Most of them, vast majority of them, end up somewhere in the region of 10 to the minus 10 to 10 to the minus 12 farads per metre. Now, when it comes to manufacturing and engineering, when we have absolute values for different measurables that end up with orders of magnitude 10 to the minus 10, 10 to the minus 12, that kind of area, it quite often becomes easier to compare different materials to use what's known as a relative value. So what we're going to do is we're going to define relative permittivity, where we are measuring the permittivity relative to a vacuum. Combining those into an equation then, we can say that the relative permittivity is the absolute permittivity divided by the permittivity of free space. So the absolute permittivity divided by the permittivity of free space gives us the relative permittivity. Now, from a units point of view, we can already see that absolute permittivity has a unit of farads per metre. Permittivity of free space has a unit of farads per metre. And what that means is that the relative permittivity is dimensionless. Rearranging the relative permittivity equation then by multiplying both sides by the permittivity of free space, we can see that absolute permittivity is the relative permittivity multiplied by the permittivity of free space. When we substitute that back into the equation in the top left hand corner, so C is epsilon A over D, the equation that we end up with is C is equal to epsilon R epsilon naught A over D. And that then is our equation for capacitance of a capacitor. Now, just to give you an idea of some values for relative permittivity, there's absolutely no need that we need to learn these whatsoever in an exam or anything. They're going to be either given to you or you'll be working them out yourself, just for illustrative purposes really. When we're talking about a vacuum, by definition, the relative permittivity is 1. Now, for air, sort of bog standard air at normal temperature and pressure, we're looking at 1.00059. Now realistically that number 1.00059 very close to being 1. It's obviously 1 to at least a third significant figure there, so we can take it as being approximately equal to a vacuum in most cases. Just to give you a couple of other examples, if you just take normal paper, so if you just grab a sheet of paper from your notebook or something like that, obviously there are a lot of variables in here, depends on the thickness of it, density of it, all that kind of stuff, but a sort of standard value for paper would be around about 1.4. For polythene, in other words, carrier bags, bin bags, that kind of stuff, again you're looking around about 2.3 for relative permittivity there. If you go up to water, water has quite a high relative permittivity, again depending on what pressure it's at, what temperature it's at and all that kind of stuff, but a sort of standard value for the relative permittivity of water might be somewhere 81 or at least in the low 80s, somewhere around there. So just to round off the video, just to dot some I's and cross some T's on this. Firstly, let's go back to the equation. So C is epsilon R, epsilon naught A over D. Obviously, one thing we haven't looked at in much detail so far is unit. So let's just round that off. Well, epsilon R we know is dimensionless. Epsilon naught has the unit of farads per metre, area metres squared, and separation of the conductors will be measured in metres. Now when we look at that, obviously we've got metres occurring in 3 of the different variables, and they actually end up cancelling each other out all across the board. What we end up with is per metre from epsilon naught. We're multiplying that by metres squared from the area, and we'll also be dividing by metres, or we can multiply by the inverse of that instead, so we're multiplying by metres to the -1 from D as well. And when you do that, when you add up all your indices, -1 plus 2 plus -1 ends up as 0 anyway, so that gives us metres to the 0, and that makes it dimensionless as well, so they all cancel each other out, and what we're left with for the unit of capacitance is just capital F, which is the unit farad, named after Faraday. Now the farad itself as a unit is quite large, so 1 farad would be an extremely large capacitance. Therefore, the vast majority of the time you will have SI prefixes to go with the unit. And again, in manufacturing quite a lot of the time, you will see microfarads being used as a standard. Even if they give an answer of something like 10,000 microfarads, we obviously know that that's 10 millifarads or 0.01 farads, but like I said, the industry standard does tend to be to give values for most capacitors in terms of microfarads. Obviously we're not going to look at it in this video, but in the next video we will start looking at putting capacitors into a circuit. Therefore we do need to know the circuit symbol. The circuit symbol is just 2 parallel lines of equal length like that. So here then is your question for this video. What is the capacitance of a capacitor made from two conductors 30 metres long and 2 centimetres wide, separated by 0.25 of a millimetre of polythene? And just to give you the relative permittivity of polythene as 2.3. Now, as usual, pause the video at this point, go away, calculate your answer and come back when you're done. So hopefully you found that one relatively easy. So let's do the equation. Epsilon r epsilon naught a over d, and let's just start plugging some numbers in. So epsilon r is 2.3 as given, permittivity of free space 8.85 times 10 to the minus 12. Now for the area, we might as well just plug the numbers straight in. So it's 30 metres multiplied by 2 centimetres, which is of course 0.02 metres. And then we're going to divide all of that by 0.25 millimetres, or 0.25 times 10 to the minus 3. When we plug that all through our calculator, we end up with an answer of 4.8852 times 10 to the minus 8. We'll round that. Probably technically we should round it to two significant figures looking at the question, so let's just call that 4.9 times 10 to the minus 8 farads, or we can say that that is 49 nanofarads. So to summarise then, in this video we've looked at capacitors. What is a capacitor? Well, a capacitor is just a device in an electrical circuit designed to store charge. It's made up of two parallel conductors separated by a dielectric, where a dielectric is some form of insulator that is able to be polarised. Finally then, once we took all that structure and worked it all through, we got the capacitor equation, which is C is equal to epsilon r epsilon naught a over d, where C is the capacitance and is measured in farads. So that's it for this video. As usual, if you've got any queries, any questions, please don't hesitate to get in contact with me. Otherwise, I'll see you in the next video.